Welcome to this NPTEL lectures on dynamics and control of mechanical systems. In the last week, we had looked at how to derive equations of motion, and we had given many examples of the equations of motion of multibody systems. In this week, we'll look at simulation of multibody systems. My name is Ashitava Ghoshal. I am a professor in the Department of Mechanical Engineering in the Center for Product Design and Manufacturing and also in the Robert Bosch Center for Cyber Physical Systems, Indian Institute of Science, Bangalore. In this week, there will be 3 lectures. In the first lecture, we will introduce and discuss what is simulation and a little bit of recapitulation of what was done previously. Then I will show you some examples of the equation of motion. Most of them are what we derived last week. In lecture 2, we will look at the inverse dynamics and simulation of equations of motion. There are 2 kinds of simulation of multibody system. One is called inverse dynamics and one is the simulation of equations of motion. And in the last lecture in this week, we will look at simulation using computer tools. So lecture 1, introduction and recap and examples of equations of motion. So in overview, in kinematics, we do not consider the cause of the motion. We look at the geometry of motion, basically. In dynamics, the motion of a rigid body or a multibody system due to external forces and or moments are considered. The main assumption is that the multibody system contains only rigid bodies. There is no deformation in the bodies which make up the multibody system. The motion of the rigid body are described by ordinary differential equations, also called equations of motion. So if the elements of the multibody system are rigid, then we will get ordinary differential equations. There are 2 methods to derive the equations of motion, which we had looked at last week. One of them is called as the Newton-Euler formulation and the other one is the Lagrangian formulation. In the Newton-Euler, we obtained linear and angular velocities and acceleration of rigid bodies, of all the rigid bodies in the multibody system. We obtained the free body diagrams and then we used Newton's law and Euler's equation to derive the equations of motion, and in between we had to eliminate the constraint forces. In the Lagrangian formulation, on the other hand, we obtain the kinetic and potential energy of each rigid body, obtain the scalar Lagrangian, and then we take a set of partial and ordinary time derivatives, and then we collect all the terms in a particular manner and we get the equations of motion. Each of these 2 formulations, Newton-Euler and Lagrangian, they have their own advantages and disadvantages. So we had looked at some of these advantages and disadvantages earlier. So basically in the Newton-Euler, we need to compute both position, velocity and acceleration, and in Lagrangian formulation we can just stop at velocity because it's an energy based formulation and we need to only use kinetic and potential energy. One of the disadvantages of Lagrangian formulation is that the constraint forces at the joints which do not do work require some effort to obtain what is the nature of the constraint forces and what do these constraint forces imply. So let us continue with overview. There are 2 main problems in dynamics of multibody systems. The first is called the direct problem. The direct problem, we obtain the motion of the rigid bodies which make up the multibody system given the applied external forces and moments. And in the inverse problem, we obtain the joint torques and forces required for a desired motion of the rigid bodies. So what do we have? We have the equations of motion. They are basically ordinary differential equations which says that the torques or the forces are given by some mass times acceleration and so on. So in the direct problem, the torque and the forces are given to you as a function of time, and then we need to solve the equations of motion to obtain q as a function of time. Okay, whereas in the inverse problem, we are given the right hand side. We are given q as a function of time, q dot as a function of time, and maybe q double dot also as a function of time. And then we need to compute the external forces and torques, okay, which are required to obtain those q's and q dots as a function of time. So obviously, the direct problem involves the solution of the ODEs. Okay, so we have F equals ma. I'm giving you F. We need to find what is A, which is straightforward, but then you have to integrate those equations of motion to obtain velocity and position. This problem, direct problem, also is sometimes called simulation. Okay, so we simulate the system given the external forces and moments and show how the multi-body system is moving. The inverse problem is useful for sizing of actuators and other components, and also for advanced model-based control schemes. So what do we mean by sizing of actuators? So suppose I give you a multi-body system and I tell you that these are some of the typical q as a function of time, q dot as a function of time, and q double dot as a function of time I want the multi-body systems to do. So I can put it in the equations of motion, and then I can compute the torque required to achieve those q as a function of time and q dot and q double dot. Okay, so hence by doing these computations or doing these work, I can tell you how much is the torque required, and which basically means that I can tell you what is the motors or actuators that you require such that you can achieve the desired motions. The same idea is also used in model-based control schemes, which we will not go into too much in this course. Anybody who is interested in model-based control schemes, they can look at some courses in robotics. In both these problems, direct and inverse, we are interested in computational efficiency. Basically, the aim is that we want to solve these two problems in a way such that it is scales with the number of links. So if I have some effort required for, let's say, n links, so let's say 5 links, and if the number of links becomes 10, then the effort should only double. It should not become square or cube. Okay, so there are algorithms which are available for multi-body system which are ON. So that is basically they are linear in the computational complexity is linear in the number of links. Okay, sometimes it is important to have algorithms which are log n complexity. Okay, where n is the number of rigid bodies. So this is possible if you do parallel computing, which we are not going to discuss in this course. And sometimes this parallel computing is required if you have very large number of rigid bodies. So there is a problem called protein folding, which is very important in many biology and computational biology areas. So you have large number of amino acids and proteins inside a protein, and these amino acids can be modeled as rigid bodies, and they are connected together. And in a protein, you can have something like 100 or even up to 500 such rigid bodies. So we cannot really worry about if you have an algorithm which is not very good. Okay, so we need very efficient algorithms to solve the motion of such long chains as in a protein. Anybody who is interested in computational biology, you can see this book. This is a very nice book, Clay-Pace et al., published in 2002. The dynamics of a parallel system, however, is much more complicated, and the complication is basically due to the presence of closed loops. Okay, the main complication or the main difference between a serial chain and a parallel system is that in a serial chain, we have only ODEs, we have only ordinary differential equations. However, in a parallel system or a parallel chain, we have ordinary differential equations arising from the Lagrangian formulation or any other formulation, but we also have loop closure constraint equations which are algebraic. So what we have is what are called as differential algebraic equations, and these are much more difficult to solve. In the rest of this lecture, we'll look at examples of equations of motion of multi-body, rigid body systems. The first example is that of a planar 2R manipulator. It is also sometimes called as a double pendulum. So it consists of two links. So this is link 1 from here to here, and this is link 2. The gravity is acting along the fixed y-axis opposite to the fixed y-axis, and this is the x-axis. The z-axis is coming out of the page. The link 1 can be described by a mass m1, length L1 from here to here. The location of the CG is at this point. It is R1 along the length, and this is just for simplification. And the z component of the moment of inertia is denoted by I1. Okay, this link can rotate about the z-axis by an angle θ1. The second link is link 2. It can be described or represented by a mass m2, the length L2. The location of the CG is at a distance R2 from this origin, and the moment of inertia about the z-axis for this link is I2. The first link can rotate about the z-axis by θ1. The second link has a relative rotation angle θ2. So it is the simplest possible serial chain. As I said, there are two moving bodies, two joint variables θ1 and θ2. There are two joint torques which are acting at the first and the second joint respectively. These are τ1 and τ2. As I said, the gravity is along the minus y0 axis. m1, L1, R1 and I1, I equals 1, 2, denote the mass, length, CG location, and the IZZ component of the inertia matrix respectively. The motion of this 2R manipulator or the double pendulum is in a plane, so hence only the IZZ component of the inertia is relevant. So let us continue. For the planar 2R manipulator, we can obtain the equations of motion. The equations of motion are two nonlinear ODEs. In the standard form, they are given as some τ1, τ2 equal to some matrix into θ1 double dot into θ2 double dot. It's a 2 by 2 matrix plus a vector which contains θ1 dot, θ2 dot, θ2 dot square, 2 θ1 dot, θ2 dot, θ1 dot square, and another term which contains the gravity. So it is like m2 r2 g c12. c12 here means cos of θ1 plus θ2. So in the above equations, this is a 2 by 2 mass matrix. It's a symmetric positive definite matrix. So this mass matrix is multiplying θ1 double dot into θ2 double dot. Then this vector 2 by 1 vector contains quadratic terms θ1 dot square, θ2 dot square, and θ1 dot, θ2 dot. These terms represent the centripetal and Coriolis terms. And then we have this gravity term. So these equations were derived in the last week, and I've also showed you how we can derive these equations in an error-free manner using Maple. As mentioned earlier, and because we are using the Lagrangian formulation to derive these equations, friction and dissipative terms are not there in this equation. Okay, if I want to add friction and dissipative terms to these equations, we have to do it in an ad hoc manner. So we have to add some friction term after this. Okay, so the friction term will be like maybe C1 plus C2 theta 1 dot. Okay, if you assume that the friction is constant plus some term which is like viscous friction. Similarly, we can have some other C1 plus C2 theta 2 dot for the second equation, but that has to be added manually in an ad hoc manner. The Lagrangian formulation does not automatically give you the friction and dissipative terms, and we have discussed this earlier. The Lagrangian formulation is for conservative systems, not for dissipative systems. Similarly, for this closed loop simplest possible mechanism, which is a 4-bar mechanism, we can derive the equations of motion. Remember, it is a 1 degree of freedom closed loop mechanism. There are 3 moving bodies, 1, 2, and 3. We have only one actuation, so that is this torque tau 1, and it is rotating theta 1. The other 3 angles, phi 1, phi 2, and phi 3, they are passive. Okay, there is only one single actuating torque. So similar to this previous example, for each link we have M1, L1, R1 and I1, and again I1 is the Z component because this is a planar motion. For link 2 we have M2, L2, R2 and I2, and for link 3 it is M3, L3, R3 and I3. These angles are given in this form because we are assuming that we are using relative angles. So theta 1 is relative to this x1 and phi 2 is relative to the direction. This is the direction of the link and the next link is this. So if you assume, or if you take the convention that counterclockwise is positive, phi 2 will be like this, phi 3 will be like this, not this smaller angle. It doesn't matter. Eventually, if you stick to a consistent configuration convention, then you will get everything will be fine. And again, there is a gravity which is acting in this direction, and the location of the CG is along the link, similar to the previous case. So the geometry and inertial parameters of the rigid bodies are M1, L1, R1 and I1 for I equals 1, 2 and 3. So there are 3 links. And again, IZZ component of the inertia matrix for each body is relevant. IXX and IYY is not relevant because the motion is in the one plane. So we have to derive the equation of motion, we break this 4-bar mechanism at O3. Okay, so we break it here, and as a result, once you break it, you will have a 2R chain, a serial chain, and a 1R chain. Okay, very simple. We have done this earlier also when we looked at the kinematics of a 4-bar mechanism. So the equations of motion or the can be very simply derived for this 2R chain and this 1R chain. So this kinetic energy of the planar 2R is very similar to what we did earlier, okay, a few minutes back. So all we need to do is theta 2 has to be replaced by phi 2. So this is a 2R chain, and where the variables are theta 1, and instead of theta 2 we have phi 2. And this is a single link with 1 degree of freedom, which is phi 1 or 1 rotation. So the kinetic energy of the 1R is 1/3 M3 R3 square phi 1 dot square plus half I3 phi 1 dot square. So this is like half I omega square, and this is like half mvc square. So the center of mass is somewhere here at a distance r3. So the velocity will be r3 into phi 1 dot. Okay, r3 into phi 1 dot. So the kinetic energy will be half m3 r3 square phi 1 dot square, and of course half I omega square, where I is the Z component of this link about the CG. So the total kinetic energy will be the sum of the kinetic energy of this 2R chain and plus 1R chain. So this first 4 terms very similar to what we have derived earlier, is for the 2R chain, and this last one is for the 1R chain. And as before, we see that there are terms which are like m1 r1 theta 1 dot whole square, I1 theta 1 dot square, I2 theta 1 dot plus phi 2 dot square, because now we are replacing theta 2 by phi 2. And also we have a term which is cosine of phi 2, which depends on cosine of phi 2. Previously in the 2R example we had cosine of theta 2. So as I said, all we need to do is whatever the equations we have obtained for the 2R, we replace theta 2 by phi 2. The potential energy is also a scalar, and it is nothing but the potential energy of this 2R chain plus 1R chain. So this will be like m1g r1 sine theta 1. We are assuming that this is the zero potential energy surface. So the CG of this link 1 is at a distance r1. So the height is r1 sine theta 1. So we'll get r1 sine theta 1 into m1g. The height of this link 2 is L1 sine theta 1 plus L2, R2 sine theta 1 plus phi 2. And what is the height of this third link? It is L3 R3 into sine phi 1. So we can very easily compute what are the potential energies of 2R and 1R, and we just add them. And once you add them and do the Lagrangian formulation, we can obtain the equations of motion. And this was discussed last week also. So I showed you how we can obtain all the terms in the equation of motion using Maple. And that is exactly what has been done here. So we have used Maple to derive the kinetic energy, the potential energy, and then assemble them together, and we obtain three equations of motion. So there's a tau 1, which is given by functions of some I2 and m2 r2 square, and then all this theta 1 double dot, and then I1 and m2 l1 square, exactly the same as earlier. And similarly one tau 2, which is given by I2 plus m2 r2 square into theta 1 double dot, and then one theta 1 dot square, and then some gravity term. Here also you can see that there is a gravity term which is m2 r2 cos theta 1 plus phi 2 into g. So here it is written slightly differently. The g is taken out. So, and the third equation is m3g r3 cos phi 1 plus m3 r3 square plus I3 into phi 1 double dot. So we can derive the equations of motion of this system, which is planar 2R plus 1R, because remember we have broken it. So these are three nonlinear ordinary differential equations. The important thing is the third equation in its current form here is nowhere connected to the first two equations. So you see here tau 3 is there, phi 1 is there, and phi 1 double dot is there. We know there is only one independent variable because it is a 1 degree of freedom system. So we need to somehow bring in the constraints now, and then all these three equations will become coupled. So right now the third equation is not related to the other two, but once you bring in the constraint equations, it will become coupled. So here it is broken. So as you can see, so the equation for this and equation for this, somehow we have to go back and couple them together. So how do I obtain this coupling? We go back and look at the constraint equation. So what are the constraint equations? It is x is L1 cos theta 1 plus L2 cos theta 1 plus phi 2 is L0 plus L3 cos phi 1. Okay, this is seen earlier. Y component is of that point where we have broken is L1 sin theta 1 plus L2 sin theta 1 plus phi 2. That will be equal to L3 sin phi 1. Okay, and we can differentiate these equations, and then we get this 2 by 3 constraint matrix. So when you differentiate the first one, you will get minus L1 sin theta 1. Okay, so partial differential with respect to theta 1, then partial derivative with respect to theta 2, phi 2, and the partial derivative with respect to phi 1. So the first partial derivative, so once you take it on this side, will become sine phi 1, and then this one will be minus sine phi 1 partial derivative with respect to phi 1, we'll get minus L3 cos phi 1. So this is a 2 by 3 matrix. We can obtain the derivative of this matrix and write the constraint equations. So this is psi into q dot is equal to 0. When you take the derivative, we have psi into q double dot plus psi dot q dot equal to 0. And this again we have discussed earlier. So we introduce Lagrange multipliers for this loop closure constraint equations. Then we get an equation of motion which looks like q double dot is m inverse tau minus c q dot minus g plus m inverse psi transpose lambda. We substitute q double dot back in the constraint equations, then solve for lambda, and then obtain the equations of motion. Okay, so this has been done earlier. So this is just a review. I have shown you what we can do using Maple, and we can obtain all these terms, and then we can obtain these equations of motion. So in this figure, just to go back and see the steps, I have broken this joint at joint 3. So then the x coordinate of this point here is L1 cos theta 1 plus L2 cos theta 1 plus phi 2. So this is the x coordinate here. This will be equal to L0 plus L3 cos phi 1 component along the x-axis. So both of these two will be equal. So for y, we have L1 sine theta 1, which is the vertical height, and then this is L2 sine theta 1 plus phi 2. That should be equal to L3 sine phi 1. So these are the two loop closure constraint equations when we break it at joint 3. And then again, we take the partial derivatives and find the constraint matrix. Then we take the derivative of psi into q dot is equal to 0. We get psi q double dot equal to 0 plus psi dot q dot equal to 0. And then mechanically, very straightforward. It's a lot of effort, but nevertheless, it's a very mechanical way of deriving the equations of motion. Okay, so hence we obtain the equations of motion, and for this 4-bar mechanism in this form, which is mq double dot equals to f minus psi transpose into a matrix which is psi m inverse psi transpose minus 1, and then psi m inverse f is given by this expression, plus psi dot q dot. The last example or recapitulation of equation of motion is that of a thin disk. So we have a thin disk which is originally in the xz plane, okay, and then there is a rotation theta 1 which is called the heading, so rotation about za axis. Then the next rotation is about theta 2, which is about the x-axis, moved x-axis, and then the final spin, which is theta 3, which is about the moved y-axis. So basically we have generalized coordinates for this problem as x, y, z, theta 1, theta 2, theta 3. X, y, z is the center of this disk. So this is the location of this point OB with respect to OA. So that is the vector x, y, z. And because there are these 3 rotations which are happening about z-axis, then x-axis, then y-axis, so we can use this Euler angle formula, Euler angle rotations about z, x, y, and obtain a rotation matrix of this disk with respect to the A coordinate system. So this is given by ABR, and we'll have this 3 by 3 rotation matrix. And as expected, it will contain sine theta 1, sine theta 2, cos theta 1, cos theta 2, and cos theta 3 and sine theta 3 in some particular order. And again, in the last week in the Maple example, I have shown you how to derive this rotation matrix. We have done it much earlier in this course also, but using Maple we can find the rotation matrix about Z, then the subsequent rotation about X, and then the third rotation about Y. We multiply these three rotations in the order of they are occurring, and we will get this rotation matrix. Okay, so once we have this rotation matrix, we can do R dot R transpose, as shown again using this example of Maple last week. I can find out the skew symmetric matrix R dot R transpose, then from the skew symmetric matrix extract the X, Y and Z component of the angular velocity vector. Okay, so this is A omega B, angular velocity of this B coordinate system with respect to the A coordinate system. Okay, and this is the space fixed angular velocity vector. So omega X will be C1 into theta 2 dot minus S1 C2 theta 3 dot, and so on. Omega Z will be theta 1 dot plus S2 theta 3 dot. So we have all these angular velocity vectors which we can compute once we know what is the rotation matrix. Then finally we impose the condition that the velocity of this point C, which is the point of contact with respect to the A coordinate system with respect to the reference coordinate system, is 0. So this disk cannot slide in this direction. It can only roll about this dotted line. Okay, it cannot slide perpendicular to the dotted line. That is not allowed. We are solving the problem of a thin disk which is rolling without slipping. So this ABC equal to 0 will give rise to these three equations, which is nothing but x dot, y dot, z dot, which is the velocity of this point, will be related to theta 1 dot, theta 2 dot, theta 3 dot, and of course theta 1, theta 2 and so on by these three expressions. So how did I get this? Very easy. So we obtain the velocity of this point plus omega cross r will be the velocity of this point C, and then we set that equal to 0. So velocity of this point contains x dot, y dot, z dot. Omega is what we had derived in the last slide. It has omega x, omega y, omega z. It contains theta 1 dot, theta 2 dot, theta 3 dot, and the angles also. And then we simplify and we'll get these three constraint equations. Strictly speaking, there is a holonomic constraint also involved, which is that this point of contact is always in the xy plane. So basically this disk cannot leave this plane. Okay, so z coordinate of this point of contact must be 0. So if you do this, a b c equal to 0, that is automatically satisfied. So we don't really have to worry about that there is one holonomic and two non-holonomic constraints. We are taking all of them into account by these three constraint equations. So as I said, the velocity of the center of the disk OB is x dot, y dot, z dot. The inertia matrix of the disk is Ixx, which is so the disk is in the xz plane. So Ixx is equal to Izz is 1/4 mr square. The inertia about the y-axis is half mr square. These are available in any standard textbook for a thin disk. The kinetic energy can be written as half mv square, v of the center of mass of this disk, plus half I omega square. Okay, and if you do the simplifications, you will get this expression for kinetic energy, which is 1/8 mr square, and then this, then you will have some terms which is x dot square, y dot square, z dot square. This is very clear. So this 4 and 8 will cancel, and r square will cancel. So you will have half m x dot square, half m y dot square, half m z dot square. That is very straightforward. Half m vc square. The I omega square part will be a little bit more complicated, and you will get this. So this is written in a compact form. That is why this 1 by 8 mr square is taken outside, and then you have theta 2 dot square plus 2 theta 1 dot square plus 2 theta 3 dot square plus 4 into sine theta 2 theta 1 dot theta 3 dot minus c2 square theta 1 dot square. So this can be derived. Okay, once you know these elements of the inertia matrix and also what is the omega. The potential energy is mgr cos theta 2. This is also sort of clear. If you can see that this is this r. Okay, so r cos theta 2 is how much is the height above this xy plane. Okay, so we'll get mgr cos theta 2. We can obtain the Lagrangian, which is kinetic minus potential energy, and then we can continue and derive the equations of motion, and then we can take into account these non-holonomic constraints of no slip. We can differentiate these constraints standard approach. We get psi into q double dot plus psi dot q dot equal to 0. So this is like psi into q dot equal to 0. So we can reorganize this. Okay, so here q is a 6 by 1 vector. So this is psi will be 3 by 6, and psi into q dot will be appropriately, you can find the dimension. So then the equation of motion, again using the approach which we have discussed now several times with constraints, is q double dot is some m inverse tau minus c minus g plus psi transpose lambda, where lambdas are the Lagrange multipliers. There are 3 of them because of these 3 constraints. And then we can find the expression for the Lagrange multipliers, which is psi m inverse psi transpose the whole thing inverse into psi dot q dot plus psi m inverse t minus c minus g. Okay, same story, whatever we have done earlier. We can compute the Lagrange multipliers, substitute back in this second order ODE, and obtain the equations of motion. So in summary, we can derive the equations of motion of a multibody system using the Lagrangian formulation. We can obtain error-free equations of motion using symbolic computer algebra systems such as Maple. And in this lecture, I have shown you the equations of motion of a planar 2R serial chain, the equations of motion of a planar 4-bar closed loop mechanism, and also the equation of motion of a pure rolling of a thin disk. So this one there are no constraints. This one there are loop closure constraints, which are holonomic constraints. And in the case of this pure rolling of a thin disk, we also have non-holonomic constraints involving derivatives of the generalized coordinates.